Proxima Centauri b is the closest known planet beyond our solar system. It orbits the star nearest to the Sun and lies in a region where temperatures could allow liquid water to exist on its surface. For the first time in history, humanity knows the location of a potentially habitable world outside our own planetary system, and it is not hidden on the other side of the galaxy. It is right next door on the cosmic scale. At a distance of just over 4 light-years, Proxima Centauri b represents both an extraordinary scientific opportunity and one of the greatest challenges ever faced by human exploration. It is close enough to study with modern telescopes, yet far enough to remain physically unreachable with any technology we possess today. The discovery of Proxima Centauri b in 2016 marked a turning point in the search for worlds like our own. Until then, most known exoplanets were hundreds or even thousands of light-years away. They were interesting, but distant. Proxima b was different. It was nearby, it was familiar, and it immediately raised a question that has shaped human curiosity for centuries. If there is another Earth, could we ever go there? To understand why Proxima Centauri b is so important and why it may remain beyond our reach, we first need to understand what kind of world it is. Proxima Centauri is a red dwarf star, much smaller and cooler than the Sun. It is part of the Alpha Centauri star system, but it orbits far beyond Alpha Centauri A and B, alone in deep space. Despite its modest size, Proxima Centauri is an active star, producing frequent and powerful flares that flood its surrounding space with radiation. Proxima Centauri b orbits extremely close to its star, completing a full orbit in just over 11 days. Because Proxima Centauri is much cooler than the Sun, a planet must orbit very close to receive enough warmth for liquid water to exist. From what astronomers can measure, Proxima b receives roughly the same amount of energy from its star as Earth receives from the Sun. The planet is slightly more massive than Earth and likely rocky. It may have an atmosphere, it may have oceans, it may even have conditions suitable for life. But Proxima b also faces extreme challenges. Its close orbit means it is probably tidally locked, with one side permanently facing its star and the other locked in eternal darkness. It is also exposed to intense stellar flares that could strip away an atmosphere or bathe the surface in radiation. In many ways, Proxima Centauri b is both promising and hostile. It sits in the right place for liquid water, but it lives under a violent star. Even so, it remains one of the most compelling targets in modern astronomy. For centuries, human exploration has followed a familiar pattern. We crossed oceans, we mapped continents, we landed on the moon. We sent robotic explorers to Mars and beyond. Each generation pushed a little farther into the unknown. Interstellar space, however, is different. The distance to Proxima Centauri is about 4.24 light-years, roughly 40 trillion kilometers. That number is so large that it defies everyday understanding. Light itself, the fastest thing in the universe, takes more than 4 years to make the journey. The fastest spacecraft ever built would take tens of thousands of years. Voyager 1, launched in 1977, is currently the most distant human-made object. It travels at about 61,000 kilometers per hour. At that speed, it would take more than 70,000 years to reach Proxima Centauri. Even NASA's Parker Solar Probe, the fastest spacecraft ever constructed, would still need more than 6,000 years to reach the nearest star. This is the fundamental problem of interstellar travel. Space between the stars is not just large, it is vast beyond human scale. Modern physics places a hard limit on how fast anything can travel. Nothing with mass can move faster than the speed of light. This is not a technological barrier. It is a property of the universe itself. To reach Proxima Centauri b within a human lifetime, a spacecraft would need to travel at a significant fraction of light speed. At 10% of the speed of light, the journey would take more than 40 years. At 20%, just over 20 years. At half the speed of light, less than a decade. But accelerating even a tiny spacecraft to those speeds would require more energy than most nations produce in a year. And slowing down at the destination would require just as much energy again. One of the most ambitious proposals for interstellar travel is Breakthrough Starshot. The idea is to build a fleet of tiny probes, each weighing only a few grams, attached to ultra-thin light sails. A powerful laser array on Earth would push the sails, accelerating the probes to about 20% of the speed of light. In theory, such probes could reach Proxima Centauri in around 20 years. But even this extraordinary concept has severe limitations. The probes would not slow down. They would fly through the Proxima system in a matter of hours. They would have only minutes to collect data, and they would then spend years transmitting that data back to Earth across interstellar space. These probes would not land on Proxima B. They would not sample its atmosphere. They would not search for life. They would simply pass by, offering a brief glimpse of a world that remains otherwise unreachable. Slowing down is one of the greatest challenges of interstellar travel. A spacecraft moving at a significant fraction of light speed carries enormous kinetic energy. To enter orbit around Proxima B, it would need to shed that energy. But there is no atmosphere to brake against, no nearby planets for gravity assists, and no fuel depots waiting in deep space. Any spacecraft capable of reaching Proxima B with current or near-future technology is likely to be a flyby mission, not a true visit. There is also the problem of time. A journey lasting 40 years would span an entire scientific career. A journey lasting a century would outlast a generation. A journey lasting 1,000 years would outlast civilizations. Any serious attempt to explore Proxima Centauri B would require a level of long-term commitment that humanity has never before attempted. The people who designed the mission would never see it arrive. The engineers who build the spacecraft would never receive its data. The society that launches it might not exist when the mission ends. Communication presents another challenge. At a distance of 4.24 light-years, every signal sent from Earth takes more than 4 years to arrive. Any response takes another 4 years to return. Commands cannot be sent in real time. The spacecraft would have to operate almost entirely on its own. Even transmitting a single high-resolution image back to Earth would require enormous power and years of transmission time. And then there is the environment around Proxima Centauri itself. Proxima is a flare star, prone to powerful outbursts that release enormous amounts of radiation. These flares could damage spacecraft electronics, interfere with communication, and strip atmospheres from nearby planets. Any probe entering the Proxima system would face conditions far more extreme than anything encountered in our own solar system. Despite all of this, Proxima Centauri B remains one of the most studied exoplanets known. Astronomers analyze the light from its star, searching for subtle signs of an atmosphere. They look for hints of water vapor, oxygen, carbon dioxide, and methane. They model its climate and surface conditions. They attempt to understand whether it could sustain liquid water over long periods of time. Future telescopes, including the extremely large telescope and next-generation space observatories, may one day provide direct images of Proxima B. We may see its clouds, its surface, and perhaps even its oceans. But seeing a world is not the same as reaching it. Human exploration has always been driven by the promise of return. Sailors crossed oceans knowing they could come home. Astronauts went to the moon knowing Earth was only days away. Even future missions to Mars are designed with return in mind. A journey to Proxima Centauri B would be different. Any crewed mission, if it were ever possible, would likely be one way. The travelers would leave Earth forever. They would die light years from home. Proxima Centauri B represents both possibility and limitation. It shows us that habitable planets may be common in the galaxy. It shows us that Earth is not unique. And yet it also shows us how vast the universe truly is. We live in a galaxy with hundreds of billions of stars. Many of them host planets. Some of those planets may resemble Earth, but between us and them lies a gulf of space that may never be crossed. Proxima Centauri B is close enough to inspire dreams of other worlds. It is distant enough to remind us of our place in the universe. It is a world we may come to know in extraordinary detail. We may map its surface. We may study its atmosphere. We may search for signs of life. But it may always remain a world we can only observe from afar, a nearby planet, a familiar star, and a journey that may forever lie beyond our reach. Proxima Centauri B reminds us that the universe is filled with worlds waiting to be understood. It shows how close we are to other planetary systems, and at the same time, how difficult it is to cross the space between the stars. In the coming decades, new telescopes will reveal more about this distant planet and others like it. But for now, Proxima Centauri B remains a destination for our instruments and our imagination, not for our spacecraft.